Module 7 Investigation 5. Using the sine and cosine function in applied settings. Jose extends his arm straight out, holding a 2.3-foot string with a ball on the end. He twirls the ball around in a circle with his hand at the center, so that the plane in which it is twirling is perpendicular to the ground. Answer the following questions, assuming the ball twirls counterclockwise, starting at the 3 o'clock position. Label quantities on the diagram that could be used to describe the position of the ball as it rotates around Jose's hand. So the ball rotates this way. And so when the ball is, say, right here, what quantities could we use to measure or describe the ball's position? The first thing that comes to my mind is an angle. So if we have our initial ray here, here's the terminal ray, and this angle theta, we could measure in radians or degrees. Another thing that comes to mind is the horizontal distance from Jose's hand to the ball, meaning this distance. Also, the vertical distance, let's see, you could say it from his hand to the ball, measuring from here to here. Yeah, we could use that, and that would be in feet. We could have also drawn that vertical distance here and said the vertical distance above the horizontal diameter. And also we could describe the arc length measured in radii or radius lengths, and that would be in units of feet, or you could have units of radii, and radii, that's just how many radius lengths that we have. Define the algebraic form of the function f that relates the ball's vertical distance above Jose's hand in feet. That's the distance that we've drawn right here, as a function of the measure of the angle swept out by the ball and the string, measured in radians, as the ball twirls counterclockwise from the 3 o'clock position. So first let's talk about the relevant variables. Theta will be the measure of the angle swept out by the ball and string in radians. And let's let d represent the ball's vertical distance above Jose's hand in feet. Then if we wanted to find a function, let's just call it f. We want the ball's vertical distance d as a function of theta. The measure of the angle swept out. Now this function, let's see, remember that the vertical distance, if we're on the unit circle, is sine of theta. If we're not on the unit circle, it's the radius times sine of theta. And in this case, our radius is 2.3 feet, the length of the string. If we're not on the unit circle, what sine of theta would tell us is the percentage of the radius that that vertical distance is. So if we take the radius 2.3, multiply by the percentage of the radius that our vertical distance is, then we'll get the actual vertical distance. Now suppose the ball that Jose was twirling travels 1 radian per second. How many radians does the ball sweep out in t seconds? Well, it seems pretty obvious that that'll be t radians if we're sweeping out 1 radian every second. Then in t seconds, the ball will sweep out t radians. Define a function g that relates the ball's vertical distance above Jose's hand as a function of the number of seconds elapsed. Okay, so we have this ball. It's moving in circular motion. We already have a function in terms of the number of radians, but now we want a function in terms of the number of seconds. But since 1 radian is swept out every second, this theta is the measure of the angle swept out by the ball of the string in radians, our function would be just the same if we replace the number of radians with t. So the only new variable that we need is let t be the number of seconds. Let's see, since the ball began swinging. And then our function is just, again, d equals g of theta, or 2.3, I'm sorry, not theta, it's going to be t this time, because we want it in terms of seconds rather than radians. 2.3 sine of t. So because we travel 1 radian each second, then our function will be exactly the same, except we can use time instead of radians. Over what time interval does the ball complete 1 revolution? So if we wanted to go 1 revolution, that would be 2 pi radians. And since we're traveling the same number of radians, like the number of radians we sweep out is the same as the number of seconds, then the time interval will be over 2 pi seconds. 2 pi seconds for 1 complete revolution. You could also write the interval something like this. Those are our inputs from 0 to 2 pi. Now suppose the ball travels 2 radians per second. How many radians theta does the ball and string sweep out in t seconds? So the number of radians theta would be equal to 2 times the number of seconds. Define a function h that relates the ball's vertical distance above Jose's hand as a function of the number of seconds elapsed. So our function d, which is h of t, the vertical distance would again be the radius times sine of theta, but it's going to be sine of 2t instead of sine of theta. On what interval does the ball complete 1 revolution? Well, we know that we complete 1 revolution in 2 pi radians. But if the number of radians is 2 pi, then what is the number of seconds? Well, we can use this equation that we've created. And if this is 2 pi, could divide both sides by 2 and get t equals pi. So there's our over what time interval? It takes pi seconds. Because we're sweeping out double the amount of radians that we had swept out in the previous problem, the period, or the time it takes to complete 1 revolution, is half what it was previously, just pi seconds. Suppose the ball travels 0.5 radians per second. How many radians theta does the ball and string sweep out in t seconds. So theta would be 0.5 times the number of seconds, t. Define a function j that relates the ball's vertical distance above Jose's hand as the function number of the function of seconds elapsed. So we know that j of theta would be 2.3 sine of theta. Oops, that's not correct, because I want to replace the theta with t. This has really got to be a function of t. 2.3 sine of, and for every radian I have 0.5 times t seconds. And so on what interval does the ball complete one revolution? Well, 2 pi radians is one complete revolution. Divide this by 0.5. 0.5 goes into 2 pi, 4 pi times. So from 0 seconds to 4 pi seconds is the time it takes to complete one revolution. That's called the period of the function. It takes 4 pi seconds for the ball to complete one revolution. The time required to complete a revolution is called the period. And really the point of this entire lesson was for you guys to think about what the period is. Notice that in each case we could find it, like if we have this type of a function, say f of theta equals r sine of some number times theta. The period is always 2 pi over b. We saw here it was 2 pi over 0.5, and in the previous problem it was 2 pi over 2, and in the first one you could say 2 pi over 1, but we just get 2 pi because there's not the coefficient of theta or t. So if you were in a standard precalculus class, you guys would really be drilling this probably. And again, our definition of the period is the time it takes to complete one revolution, or the change in input required to complete one revolution. Oh look, I think there's a definition of period over here. The period of a trigonometric function is the interval of the input needed to complete a full cycle of output values. So once those output values start to repeat the same pattern as before, that's your period. You can think of the sine and cosine functions. Once they start to repeat the same general pattern, if you measure that interval of the input, you find the period. Note that not all functions have a period. Not all functions repeat, but trigonometric functions do. Number 6, graph the functions determined in questions 3 and 5 on the axes below. On each graph, illustrate the interval of input values on which the function values complete one full cycle. That is, the interval of t for which the ball completes one revolution, or the period. Complete the following table of values and then graph G on the given axes. Label your axes. Okay, so question 3, what was our function? I believe it was 2.3 sine t. Now there's a few ways that we can do this. We could think about it intuitively about what the vertical distance would be with that ball at each of these radius links, or we could just make sure our calculator is in radian mode and just plug each of these into our calculator to complete the value. Now if the time is 0, there's no vertical distance that has been swept out, so the output is 0. When we get to pi over 2, that's 90 degrees, and we have one full radius length would be the height. When we're at pi, that's on the horizontal, and the vertical distance would be 0. At 3 pi over 2, we're at the bottom, 270 degrees, and so our radius, our vertical distance would be the radius, but we can say that it's negative 2.3. At 2 pi, we're at 0 again. 5 pi over 2, so that's 4 pi over 2 plus 1 pi over 2, or 2 pi plus another pi over 2. We're just back to 2 pi over 2 again, 2.3. At 3 pi, we're at 0, and then the pattern is just going to continue. So let's take a look at the graph. I need a scale. Let's go up by pi over 2's. So this will be time in radians, and each tick mark is going to be pi over 2. So pi over 2, another pi over 2 will be pi, etc. And here, we guess we can say this is 1 second and 2 seconds, so that 2.3 seconds is, oh, not seconds, we'll have to have feet. So I'm just going to do standard 1 feet and 2 feet. So we start at 0, and then at pi over 2 the height is 2.3. At pi the height is 0. Then we're at negative 2.3. Then at 0. Then at 2.3. Then at 0. Then at negative 2.3. Then at 0. And so our function looks like this. I totally should have made a larger scale, or a smaller scale, so that I'd have a larger graph. So we wanted to, let's see, label the axes, but we needed to do something else. Illustrate the interval of input values on which the function values complete one full cycle. So like I usually look at one of these points on the axes and note that it takes, is it from here to here that's one cycle? No. One full cycle is we go all the way up and all the way down and all the way back to where we started. This distance is one full cycle. And so that's at 2 pi. So 2 pi is our period. Notice we could have found that any place. We could have looked at from this point to this point. This change in time would also be 2 pi. Okay, let's move on to the next one. Complete the following table of values and then graph h on the given axes. So h of t, I believe, was 2.3 times sine of 2t. Now what's interesting is that for these are different time values, but we get the same sort of pattern. You might want to think about why that is. I'm just going to go ahead and fill this in. You can use your calculators, or you could think about the unit circle by plugging them in one at a time. Not the unit circle, our circle of the ball's motion. Let's see, we're again going to see the same sort of pattern, but if we go up by pi over 4's, then we'll see a slightly different period. Now this isn't the whole graph, this is just one period. Let's see how long it's taken to repeat. Pi over 4, 2 pi over 4, 3 pi over 4. This point is 4 pi over 4, or pi. So I could of course keep going with this to get the full graph, but the interesting thing here is that the period is now pi. And we could measure that. If we look at the change in distance from, say, this point to this one, we should also have pi. Alright, 2.3, 0.5 sine of t. 2.3 sine of 0.5 t. So maybe I should take a little bit more time with this one. I don't know. 2.3 sine of 0, or 0.5 times 0, that'll be 0. Sine of 0 is again 0, so this will just be 0. If we plug pi over 2 into that function, I think something slightly different happens. 2.3 sine of 0.5 times pi over 2. Let's see, a half divided by 2 is a fourth, so we really have pi over 4. Now, sine of pi over 4 isn't at 90 degrees, it's at 45 degrees, and the value of sine of pi over 4 is square root of 2 over 2. And if we multiply that by 2.3, we just get some weird decimal number, not the same thing as we've been getting, 1.626. So this one, they didn't make the input value so that they gave us nice radius links for output values. Instead, we get a bunch of crazy input values, but I'm going to go ahead and just fill in the rest of it. Okay, so if we graph this, I'm again just going to go by pi over 2's. These will be 1, 2, 3. So 0, 0. And pi over 2 is at 1.6. At pi, we have 2.3. Back to 1.6. Then 0. Then negative 1.6. Then negative 2.3. Negative 1.6. And 0. So all we have is one complete revolution. We can see that the period is 4 pi. The period of a trigonometric function is the interval of input needed to complete a full cycle of output values. Describe the reasoning you use to determine the period of the functions in a, b, and c. Well, all I did was I looked at when the input started to repeat. I measured from 0 to the point where the output started to repeat, and that change in input was the period. So what does the book say? It says, the interval of input needed to complete a full cycle of output values corresponds to the interval of input needed for the argument of the trigonometric function to vary by 2 pi radians. This is conveyed on the graph by the smallest interval of input needed, such that the output at the beginning and end of this interval is always the same value. Number 7. Suppose the ball and string sweeps out 3.8 radians per second. Okay, so this is a little bit different. We were doing, let's see, 1 radian per second, 2 radians per second, now 3.8 radians per second. How many radians does the ball and string sweep out in t seconds? I thought it was different. This really looks like exactly the same thing now. Theta is equal to 3.8 t. Define a function k that relates the vertical distance above Jose's hand as a function of the number of seconds elapsed. 2.3 sine of 3.8 t. Over what interval does the ball complete one revolution? 3.8 over 2 pi. Oh, sorry, I got that backwards. 2 pi over b. There's 2 pi radians in one revolution, but we're going 3.8 radians each second, so we can divide 2 pi by 3.8, and we can come up with 1.653 seconds. Number 8. Suppose you determine that it takes the ball 20 seconds to complete one revolution. Determine the speed of the ball in radians per second. So what they've given us is the period. In precalculus we usually represent that with a capital T. So 20 seconds is the period. That's the time it takes for one revolution. That means we cover 2 pi radians, the full revolution, in 20 seconds. So the speed is just the number of radians per second, 2 pi divided by 20, or pi over 10 radians per second, or pi radians every 10 seconds. Define a function m that relates the ball's vertical distance above Jose's hand as the function of the number of seconds that have elapsed. 2.3 sine of pi over 10. You could have 2 pi over 20 or a decimal form times t. Thanks.